Ben, yes, go ahead.
Okay then. So for the last, it's been 10.5 months now, there's been a bunch of things that I've been up to. Two main parts, which I'll show in the outline in the next slide. And I'll just talk about a few other things that I've been up to as well, just to show that I've actually been doing something. And so hopefully some of it doesn't go over your head. Especially at the beginning, I did try and take things on as a radar person. So some things, well, to be honest with you, to get through it, I'll probably leave the questions to the end so I can actually get through it. But so things that I will mention, I'll try and translate some things to comms to try and make it easy for some of you to understand than just to stick to strictly radar terminology. So first of all, I did one, as you know, rejected submission, conference submission. It was reworked and then submitted somewhere else. But that was on bistatic crane morale lower bounds for true time delay array resource allocation. So I'll go through that first. I won't elaborate on it now, just so I can get through this in an hour. The second part will be on the human blockage modeling. So the IEEE 802.11 AD, 60 gigahertz is extremely high for your typical Wi-Fi. So just looking at the effects of people walking around when people are deploying these Wi-Fi routers or data links, usually in indoor, but it can be outdoor also, but I'll stick to indoor here. Then just some notes on the summer job. So these final four will be very quick, very brief. Some notes on some of the stuff I did with the students for the summer jobs. There was 2 tasks. I'll speak about that. Some hardware tutorials, other research activities, and then I'll conclude the presentation or seminar, what thing you want to call it. So part 1, bistatic crane morale lower bounds for true time delay array resource allocation. That's a mouthful. So for sensing, we say bistatic reflections. For comms people, you're looking at a CSI information matrix, and each signature within that CSI information matrix resulted from a bistatic reflection, other than the line of sight. So me showing you how well you can estimate the time delay from a bistatic reflection, the phase and the angle that is received, the angle of arrival, is equivalently saying, how well can I get this signature? How fine resolution can I get my signatures in your channel CSI information matrix? So channel state information matrix. So there's equivalent. So I'll try and not make the terminology radar heavy because I know the audience is not radar heavy. So the JCAS problem here. We've got extremely large number of elements at the access point. So it's base stations here. There's a 16 by 16 MIMO antenna system here. And how much power does that system have to give to each of its users for them to get enough CSI information? That's the question. And now we're going up into the millimeter wave, almost in 5G. There's the already established bands at around 29 gigahertz, which is almost at millimeter wave. You're getting the capability to fit antenna elements, multiple antenna elements on user equipment on smartphones. So I've shown 2 examples of user equipment with antenna arrays, but the vast majority I've seen on IEEE Explore are typically small multiband patch antennas on the small faces of the smartphone. So which is quite intuitive because there's less likely the smartphone is going to be on a flat edge on the table, on a platform, covering all the elements if they're all on the smallest faces rather than the largest faces. But there was a few examples where it's very system on a chip, very small solutions where they have antenna arrays within a chip on the phone. So on the right-hand side, you've got 2 integrated circuits, system on a chip devices. But I will still say it's easier to block the right-hand side with your fingers and your hands than the left-hand side. It's more distributed around the phone. But in basics, I'm trying to ask the question, how much power should the base station provide and how many elements does a smartphone need to get adequate CSI information? So when I say bistatic reflections, I'm basically saying instances within your channel state information matrix. So I've just said there's no you can't really tell, or there probably isn't on this one in particular, how these elements are connected up. So you can see the elements on the surface, but how these elements connected up. So if you want to have an antenna array with a single ADC, so single channel, so you don't want an expensive multi-channel system on a smartphone because it won't be affordable for mass production. There is other ways you can do it, but the two ways I'll describe here is the true time delay array, which is basically having extremely large time delays on each element. So each element, the progressive time delay is large enough that you start separating the subcarrier frequencies into different angles. So that's one way of having a cheap, no extra electronics to control the array. But the bad thing about this true time delay, having these path lengths at each element, is the path lengths need to be quite large. And only when you get to the upper end of the millimeter wave region into terahertz do they become small enough to fit on a smartphone. But it's a possible solution to have an array with a simple system with one ADC attached. Another more prominent, which I became aware of about five months ago, is the time modulated array. So you've probably seen many times switches on the elements, and you're having a control board sending a switching pattern to these elements, and you can create a variety of antenna patterns, and that also only needs one ADC. So the people that are going to make this happen in industry are going to be more well, not worried, but they're going to make sure that it's affordable. And these two are methods of keeping the DSP and the ADC and having a single channel system. So I'll be talking about the true time delay at first, which is having large path lengths on the feeds of the antennas. The second part, I'll talk about the time modulated array, which has more degrees of freedom, which we'll talk about later. So just a little bit on the maths with the two types of arrays. Most of you have probably seen this before. So you've got the array factor of the array, and which is a summation of complex exponentials over the number of elements you have. So the bad thing about the true time delay, which is the delta PL, which is the path length difference at each element. One bad thing about this is every angle of arrival only intercepts a very small number of subcarrier frequencies. So every subcarrier frequency will be directed into a different angle space domain. So if you have a code, which is typical in a lot of comm standards, where the code is over in frequency rather than bit over in time, you can't get the full gain of matching that code because your frequency tapering over a small number of frequencies. So you're relying on knowing the code over time rather than frequency. The other bad thing, which is probably a bit towards Papain's area, is if you're shaping the side lobes, you're relying on using the amplitude H element of the array. And if you've got a power amplifier that's very efficient in one region, you don't want the same power amplifier working at different power levels because it's very inefficient. So that's another thing where the time modulated array, which has this function U or T, which is a switching pattern, that shapes the beam pattern, as you'll see next slide, by the time averaging. So the average time that each element's on, so the power amplifier is in full power in its efficient state, will give the shaping of the beam, which is a more efficient way of doing things. So two array factors. The top one relies on the delta PL, which is on the complex exponential argument at the end, being large enough to split the subcarriers into different angles, where the right one is using the harmonics of the switching pattern at different pointing at different directions in space. So here's an example of the evaluation of these array antenna factor patterns. For the first example, we're looking at 5G, which is almost in the millimeter wave band at 28.8 gigahertz, 240 subcarriers, 120 kilohertz apart. I used 11 elements for this example because the antenna one had 12 elements, so I thought I'd show one nearest and keep it odd as the one I've shown before. And as you can see, for the true time delay, which has large path lengths, in the angular domain, the different subcarriers in this standard points at a different angle because you've got a large time delay on the path lengths. I've said purposely I put the delta time delay needed. So the change in the time delay along the 11 elements needs to be 35 nanoseconds. That seems very small, but if you put that in propagation distance, it's quite a large distance. So this frequency is still quite a large, to have just a substrate integrated waveguide or just a waveguide to give you that time delay is huge. Once you get to terahertz and millimeter wave, around 300 gigahertz, that becomes very small, but we're not there yet. There's a lot of factors that go involved to making that mature enough. But let's go on to the time modulated array. So on the top right there, you've got the number of elements, so 11 elements, and you've got the time in the y-axis. So the white boxes tell you how long each element is on. And this switching pattern repeats over one, so with a duration of 1 milliseconds. So that 1 milliseconds, as you can assume, all those square discontinuous waveforms become sync patterns. They all have a complex phase component, which is dependent on the harmonic of the switching pattern. So the fundamental of the switching pattern is facing broadside, but the copied a duplicate of the signal at its harmonics is pointing at different directions. So this has got the subcarriers, and you can't get a match filter gain over frequency, only time. But this one has the harmonics of the switching pattern, and you can get the match filter gain because it's got a replica of the subcarriers just shifted at the harmonic. So that's the two things. You're dealing with subcarriers at different angles and switching harmonics at different. There's plenty of things you can do with this time modulated array. I won't go through all of them, but I'll have a brief mention later on. So I've told you the standard, I told you the array. We want full coverage. We want to look at the channel as a whole. So if any reflections are coming from different angles, we want to get information about them so we can get more information in the CSI matrix. So I've told you the standard we're using, which is the LNMDS, the 28.8 gigahertz, which is a high enough frequency to get lots of patches on the UE. When I say UE, I mean user equipment. So obviously with 5G, they're channel matching, getting optimum data rates for their users, but they're also broadcasting a signal to look for users. So when the user sends back on the uplink, it channel matches, but it's still broadcasting a pattern to let everyone know that the base station's there. So in that broadcasting, there's always going to be, for this standard, the primary and secondary codes, sync codes. So the PSS is the primary code. Then there's no transmission in between, and then there's a secondary synchronization code. A UE, a laptop, a tablet only needs 3 vectors with 127 elements. And if you put a base station into these vectors, you get a code. So it's easy enough to correlate the correct code and to know what the base station ID is. So this is the signal we've got. We've got a multi-component over 240, or in the case of the beacon, 127 subcarriers on F subscript SC. And then you've got a phase code for each of these frequencies. So let's talk about the scenarios in space. So I've tried to say each of these reflectors in radar we call bistatic reflectors. They correspond to something you see in the CSI matrix. I'll wait for this. You should have got a loudspeaker. So this corresponds to every signature you see in the delay Doppler in your CSI matrix, if you're familiar with channel state information matrices. So in radar, we just say bistatic reflectors. So it's in the simplest form, it's good to keep everything simple. Base station, transmitter, radiating a signal, the beacon signal I've just said. It hits off a reflector. The bistatic angle is correct for it to be intercepted by the receiver. So the receiver here has got the array I've just shown, which has the nearly full coverage over the plus minus pi. It's intercepting, depending on what angle that signal comes in, it will intercept at a different frequency. So wide coverage on the RX. So at the base station line of sight, it's going to intercept at one frequency. At a larger delay, it's going to intercept at another frequency. And just a bit of trig here, just the cosine rule just tells you the parameters in its simplest form. So you've got a signal being intercepted with the line of sight plus non-line of sight. Each have their own amplitudes, each have their own phases, each have their own delays, and also a different frequency, because we've got this setup where angle corresponds to frequency. So angle corresponds to frequency. I'm sure a lot of you are familiar with the spectrogram or the short time Fourier transform. This is a linear way of representing frequency and time. So you create your, if you're those who are familiar with it, you create your time frequency filter banks, and then you say which ones have correlated well with the signal, and you've got an image in time and frequency, and the filter banks, the ones that correlate with the filters have a strong amplitude, the ones that don't have don't. So it gives you a 2D image of the signal. Well, this is a linear way of doing time frequency. There's a whole bunch of transforms called quadratic time frequency transforms. The simplest one is the Wigner-Will domain, which is its origins are quite complex. I don't understand. I don't go near quantum physics or anything like that. But the Wigner-Will domain is essentially like a spectrogram. You're showing the signal in time and frequency, but because if you imagine you've got time displaced codes in both of these signals, S, ref, and S, and you've also got different subcarriers. So when you multiply those brackets out, you're going to get quadratic behavior, aren't you? You're not going to get, there's going to be more mixing than what you intended with a spectrogram. So let's just keep it simple. So where the signal is, so with a spectrogram, you get high energy where the signal is in time and frequency. And where it isn't, you get no energy because the filter bank hasn't correlated with it. Similar in this case, where the signal is, where that phase code I just said is, it correlates with itself. So you get a compressed signature in the actual frequency and time places that the signal is. But because of the quadratic behavior of this, it can get complicated very quickly with these, but I'll try and keep it simple. But because of the quadratic nature, the simple rule of thumb is where the signal is, like a spectrogram, you get your compressed sync-like patterns at the actual time and frequency content. But you also get cross terms because the brackets are multiplying out. So halfway between in frequency, you get a cross term, and halfway in time, you get a cross term. So the cross terms exist halfway between where the signal actually is. And this cross term is called, it's an interference pattern because it's a cosine. So the cosine frequency depends on the separation. So if these are really close, these auto terms, and they've been like a spectrogram, then the frequency of the cross term will be very small. But as they move further away, the cross term, the frequency increases. So this frequency gives you information of how well they're separated. Same in the time domain, but there's a horizontal frequency now. So the more they're split away, the higher the frequency is in horizontal. And also diagonally, so these are auto terms. Every two auto terms create a cross term. These create this one, these create this one. These two create the one in the middle. That's separated in time and frequencies, isn't it? So there's a diagonal frequency in the cosine. So the good thing about this, with the arrays I've just spoke about, you're creating one angle of arrival to have a frequency and another angle of arrival to have a frequency. So the line of sight has been intercepted here at this frequency, this angle. Well, this one is intercepted at another frequency, another angle. So every time you get a line of sight and non-line of sight, as you do in your channel state information matrix, if you've got non-line of sight scatterers, you get this pattern. Two cosines with horizontal frequency, two cosines with vertical, one with a diagonal in the middle. So I can create a dictionary that says, I know if for this angular separation or this frequency separation, I'll get this signature. For this change in delay, this one's been much slower going to its scatterer and coming back to the receiver, I'll get this signature. So I can create a whole dictionary of different variations of this and correlate each and say, is it more likely that it's this configuration, this angle, this delay? But also what I haven't mentioned, which was unprofessional, which is an important thing, there's phase information also. So the cosines in this, it's not just a frequency, there's a phase information. So the phase difference between the line of sight and non-line of sight is also in the cross terms. Definitely need to speed up. So all I did for this research was create these 5 cross-term signatures, look at the singular value decomposition, which I'm sure some of you are familiar with at least, take the largest feature, because one of these elements in the diagonal, or these orthogonal vectors, has a lot of the information. Intercept the signal, cross-correlate it with all these different types, versions of this, which have different angular arrival differences, different delay differences, different phase differences between the cross terms, and say which one more likely is the correct phase difference, angular difference, time delay difference here. So what's the angular difference between these, the delay, and also the phase that it reaches the receiver? And I get these patterns. So it's trivariate. There's 3 parameters. There's the bistatic angle, which I've made frequency with this arrays that I'm using, the delay, and also the phase. So if this is the results of my dictionary of all the different types of these cross-correlated with an intercepted signal, and it says this is your likelihood function. So the maximum likelihood is the largest likelihood. So these lines here, this simulated noisy signal is at 20 degrees separation with line of sight, with a delay of 15 samples in 5G samples, and a phase of plus 35 degrees. So the maximum likelihood is dead on with what it actually is. Now, the next thing is, if you've got a complicated scenario, say your channel state information has many signatures in it, the rule of thumb, well, the thing that you need to say is, the quicker this falls off, the gradient, so the larger the gradients, if you've got many of these signatures that you've intercepted, the more narrow they are, the more information there is. If they're all wide and they're all superimposed, it's difficult to get information from them. So the Kramer-Rao lower bound essentially assumes a Gaussian Gaussian sort of signature, and it's basically the Kramer-Rao lower bound is basically saying how rapid is the gradient going down, and that gives you an indicator of resolution. So some of you, if you're familiar with statistics, as I just said, I said it to try and improve for some of you if you're not familiar with this sort of theory. The Fisher information matrix is basically, as I just said, it's how quickly the gradient goes down, but it's on the second order. So the Hessian, which is the H, is the second order derivative of these functions. So the larger the derivative, the smaller the resolution. So it's an inverse. So the Kramer-Rao lower bound is the inverse of this Fisher information matrix, and importantly, it's got SNR. I'd refer you to Greco's papers or Harry Van Trees, who recently died actually, his books for all the actual fundamentals of how these are. Harry Van Trees' book's very good, and this paper is very good. So we now have SNR as a function of as variance. Actually, Kramer-Rao lower bound is a variance estimator, but root Kramer-Rao, if it's a square root, so it's a standard deviation. So now we're interested in the number of elements the UE possesses, the number of elements in the phone array, and the fractional power supplied by the transmitter. In simple, more elements, more power allocated, the lower the variance is. So this SNR is now on a denominator. So if the SNR goes up, the variance or the standard deviation here goes down, as you'd expect intuitively. And this is just the line of sight SNR and the SNR, the non-line of sight. And we're interested in this alpha. So how much power, so alpha times power, and alpha's between 0 and 1, how much alpha do we need for an acceptable performance? And obviously the number of elements is in the array factor. So the more number of elements, coherent elements, the higher the array factor is. And these are just the two. So let's just look at a simple scenario. 5G, as I just said, the 29.9 gigahertz band. Let's just say we're looking for a drone in a region of space. I took a value of a drone to be minus 10 dB square meters at 30 gigahertz from this reference. We're assuming we're intercepting the line of sight and non-line of sight. So the line of sight's going to the receiver, and the non-line of sight's going off the drone and going to the receiver. So it's the same bistatic triangle. These are all very the subcarrier numbers and spacings are from the 5G standard. The power of the base station 20 dBW is just from a typical base station. So we're just looking at what estimation capability in range, angle, and phase, because you need, if you want to get Doppler, you're looking at phase over time. So phase, angle, and delay, do you get when you give the base station a certain number of power, alpha times the maximum power you can have, 0 and 1, and you give the receiver a certain number of elements. And that's a simplified, when you put all these all together, it simplifies this SNR equation here in terms of number of elements, alpha, range the base station to the reflector, range the reflector to the receiver, and this constant. So all these is all gone into this final constant, basically, just to simplify. So this base, when I submitted the paper about 5 months ago, this is one of the plots. The range standard deviation, so how accurate the accuracy of the range, the lower bound with respect to the number of elements that the smartphone has, the angle of arrival accuracy in respect to the number of elements, and also the phase. And as you can see, the number of elements you give, if you've got a humongous tablet and you put 30 gigahertz patch antennas all over it, let's say it's 50, you got 50 on there, you're going to have sub 1 meter standard deviation, sub 1 degree angle of arrival estimation, and sub 1 degree phase estimation. But I said we're also interested in the amount of power the base station transmits in the direction of the receiver. So it's a bivariate problem. Number of elements, the amount of power the base station gives. So easy enough. Many people, when you've got multivariate problems, this is just a bivariate problem, you can use the L1 norm, L2 norm to simplify, which is just the absolute sum of a vector to have a one parameter, which includes many dimensions. So I assume at least some of you are familiar with the L1 norm. So let's say the base station has a certain specification, could be a person, could be a drone. The specification is it wants a variance or a standard deviation in range of 1 meter. It wants a standard deviation in phase of 1 degree, and it wants a standard deviation angle of 1 degree. That's the specification. He wants range, angle, and phase to be within these parameters, varying within these parameters to do its processing for classification, for tracking, whatever it wants to do. So I've included this specification. I've done all that theory I've just showed you, minus this specification, which is just for a certain task, and looked at the function, the L1 norm. So the L1 norm, which is just one, is just the absolute sum of this difference vector, gives you this surface. So discontinuity tells you there's something's gone through, there's going to be a zero crossing, there's been something. So basically this surface is showing you the lower part of this discontinuity, these circles, the white circles, is when the fraction of power and the number of elements is not good enough to meet this. When you go to the top right hand corner, it is good enough to meet that specification. So this is sort of like an optimization problem. So if you want to get to that, if you want to give the minimum amount of power and have the minimum number of elements for cost efficiency, you want to get to that boundary, don't you? Because you know that's where it started to meet the specification. So you use things such as gradient descent to get to that minima point, that discontinuity, to give the minimum amount of resource. Because in 10, 20 years, these base stations are going to be doing a huge number of things at the same time. So it wants to give minimum number of resources for each task. In practice, as I said, drone, just a simple simulation. Here's reflectivity or RCS in angle. I use the mean value. So the mean value, the mean RCS of this drone at all angles is the solution, this boundary. But if it's larger than the mean, you need less elements, you need less resources. If it's smaller than the mean, you need more resources. So in actual fact, it's going to be a moving boundary depending on the angle you're looking at the target. We've got to be super quick on the next part. Okay, so yeah, reviewer comments. One said good, one said it's acceptable, one said acceptable, and then valid contribution on all of them. But most of all, what's the most important thing about the submitting the paper? The result. Rejected. There you go. So next part. Yeah, I've got over that now. Next part. So we're looking at now millimeter wave. We're still looking at arrays, portable arrays. Now we're looking at Wi-Fi, 60 gigahertz, double the frequency, half the wavelength. We're looking at the blockage, the effect of blockages. So I've been working on this the past 4 months. Why do they have this frequency, this standard? It's been sold commercially. You can buy it now online. Large data rates, high quality video streaming with no wires, VR headsets, modern gaming requirements. Is it millimeter wave to the rescue? 60 gigahertz carrier frequency, the bandwidth is about 1.75 gigahertz. Problem is, you have high attenuation at mobile objects, people. So anywhere where the bore site of a non-line of sight or a line of sight comms link crosses a person, you're going to get a huge loss. People usually move around, especially in commute areas. So you've got a dynamic target that can cause huge losses, a big problem. So now, as I've called it here, conic billiards. So it's a game of, just a simplification. If the main lobe is dominating the side lobes, you can simplify it to like a cone function intercepting. You're basically playing billiards and trying to get the reflection to the user. Basically, that's the game. Basically, you're trying to get the optimum reflection that isn't blocked by any person, and it gets to the user. So can an AP do all that itself? Can it centralize processing? Can it do everything itself? Can it look at all these people moving around and deal with the whole situation? So JCAS, if an AP is going to do that, it needs to actually perform communications. So the channel capacity and the symbol error rate is important, but it also needs to detect things and have a good range of velocity estimates and have a low false alarm, because it doesn't want to process every time it gets a noise has gone up suddenly. So it's both communications and sensing. So this is the communications parameters and this is the sensing parameters. So if you want to know the sensing parameters, such as the probability of detection of a person, so you want to know if a blockage is going to happen, you're going to need to detect where the person is and where it's going, where he or she is going. This receive power has RCS in it. So the receive power to the AP is dependent on the reflectivity of a person. Thankfully for me, this group in India has already done a large trial of measurements, and they've found the RCS statistics over a large period, and it's log normal. So you're familiar with normal. So log normal appears normal on the logarithmic scale. If you do the back to linear, it has a huge tail. So what log normal actually means is that the values being seen at different samples changes on a logarithmic scale, and that's typical when shadowing dominates, when there's a mixture of specular and diffuse scattering, when basically when the values are changing a huge amount, even though it's the same to us, we see a person, oh, there's a person, they've turned around, it's the same person. So this 60 gigahertz frequency, the thing perceived by this radar changes on a huge value. So the statistics are log normal for the person, for the RCS here. So this is log normal, which is given by that equation on the bottom right. They've thankfully supplied the statistics so I can extract them. And we'll assume that the receiver is just an independent additive white Gaussian noise. So it's a Rayleigh distribution. So this histogram just shows the receiver noise, put an attenuator on the antenna. This is what you'll see. You'll see Rayleigh noise. You've got the I and Q channels with independent white Gaussian noise. You take the attenuator off, there's a person at 1 meters. You get power levels of around minus 80 dBm, varying on a decibel scale. This is a log normal target. So you can find the probability of false alarm of this simple situation. You put a threshold here, and then you look at the area which is above the threshold, which is just noise. So it's the noise causing alarm, which is not shouldn't do. So you do the integral of this PDF, which is a Rayleigh from the threshold to infinity. Probability of detection after you've got that threshold. So if you work this integral out and you get the threshold, I'm sure some of you have seen this equation before. You get the threshold in terms of certain probability of false alarm. For radar, 1 in a million. Sounds quite small, but it's very typical. Then you integrate the other PDS from the threshold to infinity, and that gives you the probability of detecting it. So anything below that, you're missing out. So you're hoping that's quite large. So I don't usually go with the effective radiated power. I usually stick with power transmit, power and gain. But the standards of these Wi-Fi's, they like to have effective radiated power, which is basically a combination of transmit, power and gain together. And if you do the effective isotropic radiated power, it's just a constant times this, because you're doing the equivalent geometry of an isotropic beam compared to compressed beam. So in this plot for this situation, a person indoor, you've got different routers, so different routers with different antennas, with different power transmit powers, gains, up to the standard maximum for Europe, which is 40. But then if we just consider a normal router, which is can be built, it's not a DIY router. You see many routers that have dipole antennas, and 2x2 MIMO is quite typical now. So the effective isotropic radiated power for a 2x2 dipole system is 26.7 dBm. If you go, you're going to have to build quite a, it's going to be like a hobbyist DIY system if you want to go much higher than that. So if you look on this plot, for a 4 dipoles MIMO system, which is typical, the probability of detecting a person at this standard with a 99% chance, it only is 9 meters or less. So if you go above 9 meters, if a person goes above 9 meters, you're getting a lower probability of detection than is acceptable. Actually, 99% is quite. People go above that easily. So it just shows that the distance you can detect with 99% accuracy a person is which is quite small. And then so non-line of sight, we're going to talk about non-line of sight, which is going to be very brief. So non-line of sight, you're transmitting the signal, it's going off a reflector, and you're making a comms link not directly to the person, but you're using your environment to have a non-line of sight connection. So I can use the same plot, being lazy. If I assume that the radiated power is the same and the reflector has an RCS of 0, or in linear terms 1, it's the same 9 meter distance that you can detect the person with a 99% accuracy. But obviously with non-line of sight, you've got two distances. You've got the distance to the reflector, then the distance between the reflector and where you're getting the comms link. To keep it simple, everything I show from now on, the distance between the router or the AP and the reflector and the user is going to be the same. Because otherwise you have an added geometry, and I don't want to talk about things like cosine or oval functions. If you don't know what that is, you can look that up yourself. So okay, thankfully that group showed the reflectivity of a person at 60 gigahertz using this standard. Thankfully, another group in Germany have done a measurement trials of blockages. So they did a large amount of trials. And they've seen quite a small variance. So you think this is the bore size to the antenna, and you've got a line of sight link with a person, a comms link, and another person walks across. This line here is when it's directly blocking the line of sight. So you get a maximum attenuation. But if it goes, because I don't know if you're familiar with Fresnel zones, but once it goes a certain distance away from complete direct blocking, you begin to have a linear rise again. So the person starts walking across the beam, you get a linear reduction, a flat attenuation, then a rise again when it leaves the beam. So I won't talk about Fresnel zones, but it's heavily to do with the Fresnel zones. So they got all the parameters, statistical PDFs, which they usually are statistical unless you're talking about the document format. So they got these parameters, the time between the starting to fall and the end of the rise. They fitted that to a probability distribution function. They fitted this mean attenuation to a probability distribution function, and also the decay and rise. But we'll assume it to be a symmetrical function for now. So I got all the parameters off their research. I got the times between seeing the fall in the signal, the maximum attenuation, and then the rise again. Because they give velocity, they try to keep the person having a constant velocity. You can convert all these times to distances. So I converted all these trapezoidal functions into distances. So you've got attenuation over distance relative to the bore site of the antenna. So all the statistical investigations or information they've gained, I've just converted them into a deterministic trapezoid function, as you see, with all the mean values. I don't care if it's a wide ball PDF, I just convert it to a mean, and that's what I'll use. So we plot this loss parameter in the SNR, use these 2x2 dipoles, and to get a 99% probability of detection, it's up to 5 meters. So before it was up to 9 meters, but when a person's standing in front of a user, then you only, if the user's above is further than 5 meters, you're not going to be able to detect them. I think I'm talking nonsense, actually. It's basically saying if a person is above 5 meters, you won't be able to get a good detection of them. That's what it's basically saying. They also supply the non-line of sight, so sending the signal out, someone's blocking, it hits off a reflector, then it goes to the user. So it's not going from line of sight, blocker, user. It's router, blocker, reflector, user. So non-line of sight blocker. Completely different things going on there. As you can tell, before the mean attenuation was 13 dB, having a blocker to the user directly. But when you're wanting the signal to be coherent and a blocker, so the energy goes to the user, the effect is more by having someone in between that initial reflection, because then things aren't coherent on the reflector, and it's a poor radiator into the direction. It's 10 dB more attenuation. I've talked about Kramer-Rao lower bounds before. So we're interested in JCAS capabilities of this AP that's centralized, is trying to figure everything out, where people are, stop blockages. So the beacon signal for this, what I found for this standard, was over 12 subcarriers, which was quite small. And from that theory I've just shown, the Fisher information matrix, inversion, and look at the velocity and range variances now. So the variances in range estimate and velocity estimate. Doing this theory all again, I found out this matrix gives, so at an SNR of 0 dB or 1 in linear terms, you get a range variance of 15 centimeters, no, 15 millimeters. And at the SNR of equal to 1, you get a velocity variance of around 10 meters per second, which is quite large. But to get velocity, you get a number of phase measurements first, do the FFT. So it's not a surprise it has a larger variance. So I put those trapezoidal functions I've just did, and then put the SNR. So we're looking at sensing now. So it's two-way. You want to look at your target, and it has to reflect back. So go to the target and back. So these are the two-way SNRs. And you can see it drops off significantly from 10 dB to minus 20 dB because of the presence of the blocker. And the blocker has even more of an effect when it's non-line of sight comms compared to line of sight comms. I plot these SNR, basically put these into these equations. So you have a similar sort of effect on the variance of range to estimate range, similar to estimate velocity. For comms, it's one way. It's a one-way system. You don't have to think about coming back. You want to get the data to the user. So these are the one-way SNRs. Don't be alarmed. Well, you're not going to be alarmed. The SNRs are similar, really, for one-way and two-way. The reason is the user equipment has a small receiver gain. It's only a small smartphone, small patch antennas. Receive a gain of 7.5 dBi for a patch is normal. The router had a receive gain of 14 dBi, so that's why they're not as different as you would expect them to be one-way and two-way. And I'm talking comms now, so we're interested in the symbol error rates. 16 QAM, as you'd expect for QAM compared to BBSK and QPSK. Hugely sensitive on the SNR because this drops off quite quickly, this complementary error function. So this blockage has a huge effect on the 16 QAM being able to decode it in comms. You're going from minus 50 probability of log 10 minus 50 in the log to around 1 due to the blockage effect for 16 QAM, and it's even more of an effect on the non-line of sight blockage model. The Shannon capacity, so even though that shouldn't have bandwidth, I've done it in bits per second per hertz. The quote for this standard is around 14 bits per second per hertz, but this blocker goes from around 14 at short distances to around 6 due to the blocker. So that's the Shannon channel capacity, the effect of blocking on this. But obviously the disruption depends on the user data. If they're not using it, if they're streaming high quality video, there's different. So I'm going to have to be very quick. Alternative approach. Instead of having an AP trying to work out everything that's going on, a centralized way of processing. And as you can see in the block, a person walking in a certain formation to another person, it's going to have a huge effect, isn't it? If the AP is on the other side of a blocker, what much can it do if it's on its own? So to gather all information. So the alternative approach is distributed processing. So I talked about in the first part, the UE can have an array now. The frequency is so high, the multiple antennas can fit on a phone. So why not let the UE have a look at its angular spatial domain? If it sees a blocker, it changes its uplink. Because all the router's doing is channel matching. It's channel matching what it receives. So if the UE has an array and it can look and see if the blocker is going to cause a disruption, it changes its uplink beam pattern. And all the router's going to do is channel match to the uplink. So the UE is the master in this situation, and the router's the slave, because it's just channel matching to what the UE decides to send its uplink transmission to. So equivalent to blockage starts to happen. UE says there's a block. Well, the UE detects a blockage. It changes its beam pattern to another direction. So the attenuation goes to 0. So the T react is the response time. So the shorter the response time, the larger the average of the smaller the average of the attenuation. So instead of having just letting the blocker do its whole time and disrupt the communications and sensing, it will start to disrupt. The UE will change its uplink pattern at a certain time, and then it will choose a link which has no attenuation. So you're looking at the change in the average of this effect. And these are just surfaces of response time over the sensing or comms parameter. In this case, it's the range variance. So the quicker you respond, the larger the average range variance is. This is what, and there's more of an impact for the non-line of sight case because it's more disruptive, the blocking. So the sooner, when the blockage starts happening at 0, the sooner the response time to bring it back to 0 attenuation, the larger, the smaller the variance in range. Smaller the variance of velocity, same thing. This has got a huge drop off. So you need to respond quickly. So if you don't respond in this initial falling period, there's not a huge gain. So you need to respond. The UE needs to change its pattern before it gets to this period where there's not much of a gain. So it needs to be quick. Same with the comms, so it's JCAS. If it responds within 50 milliseconds, there's a huge gain to be had. If it doesn't, there's not a huge gain to be had. And same with the channel capacity. To be very quick. So this is going to be rapid now. So talk about true time modulated arrays, having switches on each of the elements and deciding when they're on or off. You can do, it's not just on and off. There's people that have done different phases. There's a huge amount of capability you can do with this pattern. Essentially, what so with Windows, so the Chebyshev window, if you're typical with Spectrum Windows, it's flat and it falls off, isn't it? The window, it's in the spectrum. For this time modulated array, it converts this to time durations. So the middle element has a large time duration, and these reductions in time durations is equivalent to the falling off of a window, a spectrum window that you're familiar with. That's what it coincides with. And that causes a main lobe pattern to side lobe, all side lobe patterns to be minus 30 different dB difference, this windowing, ideally. So that it just simplifies the propagation. We don't have to worry about, oh, where does, if you've got an isotropic pattern, it's more, you have to think about spherical modes, or if you've got high side lobes, you have to think about where do these side lobes go, what links are they creating. But for this windowing, you only have to worry about the main lobe. So you have to follow the one main lobe and see where it goes, basically. It simplifies it. For these cones, so each main lobe is like a cone or a spherical sector. When they intercept, forget all the furniture, think about ceiling, floor, walls. There's three possibilities. The main lobe, the cone, intercepts one plane. It either intercepts a ceiling, a wall, a floor. That's it's going to be an ellipse. If you're familiar with conic sections of a plane intercepting a cone, it's an ellipse. So if it intercepts one plane, it's an elliptic radiator. And if it intercepts two planes, you're at a corner of two walls, or a wall and a ceiling. And this is in radar, we call it dihedral reflector or dihedral radiator. It can intercept three planes. Then you're talking about a bottom corner or a top corner where the walls, two walls and a ceiling, or two walls and a floor are meeting. That's called a trihedral reflector, three planes. So if we stick to the simple windowing and we're looking at one main lobe, we're either going to get an elliptical radiator, a dihedral radiator, or a trihedral radiator in a room with no furniture, to keep it simple. And we follow the cones. So each radiator creates another main lobe. You follow it until it goes below the noise floor, because the receiver can't detect it now anyway, so we've gone well over. So if the router, the transmitter, or the UE intercepts just one plane, a ceiling or a wall, and you get an ellipse because it's a cone, you get a Bessel function. If you're familiar with integrating polar coordinates, these Bessel functions of the first kind always come along in polar or cylindrical integrals. So the radiation pattern for this is going to be an asymmetrical ellipse, depending on the radius of the ellipse. Similar, all the energy, most of the energy is within one small region. So you won't have to follow one cone again, because it's all within a small number of angles. There's no distributed different. If you intercept, the beam pattern intercepts a corner of two planes, so the corner, I can't find one here, but corner of two, it's an ellipse, but the thing is you've got multi-bounce in the middle, so that's going to be a wide scattering, high scattering, but then you've got, when the phases align at the planar wave, you've also got the same Bessel functions. When the flat part's 45 degrees away, you've got three lobes here. You've got one when you're flat on with this wall, one when you're flat on with this wall, and one when you're near where there's multiple scattering. So indoor scanning for this standard. It's going to be funny. So when I show you this blank slide in a minute, I'm just leading you onto a. Anyway, so for this scanning, all these cones are being scanned in azimuth by a router. There's a thing called the beacon transmission interval. So a router will train itself where it is by scanning the room with this beacon to see where the room is and all sorts of sophisticated stuff. So basically, what I was planning to do in the next 2 weeks is to look at these, when you follow these cones around this environment, empty room, what does the power levels look like? Follow the cones again, put a person walking in the room, follow the cones again, what do the power levels look like? So it's another decision problem. You follow the cones, the radiation patterns around the room with no blocker, you get a Rayleigh. So you got the noise, which is the receiver noise, which is Rayleigh, and most of you know Rayleigh plus constant is a Rayleigh. Depending on the amount the constant is compared to the variance of the Rayleigh, these are all different Rayleigh functions, but it depends on how dominating that constant is to the variance of the Rayleigh. Fundamental stuff there. So this problem, which I plan to get something from in the next couple of weeks, is you've got no blocker. You've got a dominating component on the receiver noise, which is a Rayleigh. When you insert a blocker, when the cones, so you think about the cones, the bore site is the middle of the cone. When a person becomes dominating, causing blockages, that PDF is going to change, isn't it? So the more the blocker causes problems, the more that PDF goes towards the Rayleigh function, where it's not seeing, it's just a receiver noise. So I've got a different detection problem here. H0, which in textbooks is a Rayleigh typically because the receiver noise behaves that way in simplification. But in this case, my H0 is no blocker. That's a state. And the false alarm in this case is I don't want to start saying there's a blocker when there is no blocker. So the threshold will be somewhere and the integrals will be the other way, because you're interested when the power levels go below a threshold, not above a threshold. Previously in standard detection, when the threshold is exceeded, you start doing your processing. It's a target, it's something to look at. In this case, when the threshold is subseded, there might be a blocker. So the integrals are the other way. You're going from the threshold to minus infinity rather than the usual threshold to plus infinity. So yes, once you have these ambient DOA vectors, what power levels look like in an empty room, what do power levels look like when the blocker's here, when it's walking in a linear velocity trajectory. Then I can do these integrals and say, this is the probability, I've gone well over, but oh well. And all this is to find this function. I know if you respond in this time, this is the result now, but I don't know what the time is yet. I need to know this. I need to solve this problem to know what the time can be. But that's a simple way of looking at it. You also need to know your clock frequencies of your UE processor. There's lots of other things you should know as well. But fundamentally, you need to know when can a UE know there's a blocker, and this is the statistics that are going to allow to know that time, response time. The UE can change to a different pattern and reduce the effect of a blocker. I've gone well over. Okay. Unfinished work, and I know Yang said this from quite a while ago, and Yang hinted at this was some of this should be the forefront of the research, but I haven't tackled it. I've led towards it, but I haven't tackled it completely. Is the effect of reflected, because the the router can be in a place where it's hard to get in a small distance. It's hard. You have to climb on a ladder or something to disrupt the UE to get too close at high power levels. But in a UE, you've got it in your hand. These array elements, it's easy to block them. So there's some good work from a group in India where they've with the time modulated array. So these are the periods that each element is switched on. They've been able to show that they can create all these different beam patterns when certain elements are faulty. So here, element 31, 23, these are all they've deemed them as faulty in manufacture. I don't know how. But they've still been able to create beam patterns. But you just change the terminology for this. Instead of faulty, you just say they're blocked by the hand. So in this case, in this picture, these elements where the fingers are on, you can't turn on at all. You only can turn on the elements that are not being covered. Then you do your optimization, whatever optimization technique to get to a reasonable beam pattern to get your comms link to the router from the user equipment with only a limited number of elements. So this is pointing towards things that can be published in journals, which I haven't done, but I think the route's easily there because I haven't seen anyone that's converted this sort of theory to the UE case, fingers and hands covering certain parts of the antenna array. So, and you got the dangerous SAR. So yeah, is there any point doing this? How good are summer jobs? Part 1, did a document that had simple EM theory to help with basically replicating the EM boundaries of a person with clothing, skin, with material which the students have built in the lab, which you've probably seen. And I was able to say, instead of using, because water had such an impact on moist skin, had such a difference to dry skin at these frequencies, I said I would put fake leather, buy some water-based cleaner, and then cover it with water-based cleaner and try and replicate that sort of effect. Because at these 77 gigahertz, moist skin has a completely different EM characteristic to dry skin because of the water content. Summer job part 2, this was a failure, but I created a document to say you've got 2 boards. You know the propagation distance, the line of sight's the same. So if one's a transmitter, you send a signal, so another is a receiver. You switch them, so that the transmitter becomes the receiver becomes the transmitter. They should still see the same delay. You haven't moved anything. The signal should still travel the same amount. If there is a difference, that means they haven't been calibrated. So just a simple document that said the trigger signal should be delayed by this amount, depending on what the difference in your range or beat frequency you've seen. But no further investigations than that. It didn't work. So also helped with some measurements in KU Leuven, with in collaboration with TUE. I don't know if you use that acronym, but Eindhoven. So I didn't do the dirt. I didn't do the hard work. Kai and other people were there for the full week. They had people constant velocity, to the same point that the work I showed before had constant velocity. So you can convert the times to distance. They were doing certain walking trajectories and measuring with the radar and the comms system at 28 gigahertz. And the leading author, Bram van Berlo, got a paper out of it. So that was good. And I was able to contribute, I think, 3 range Doppler results in his paper, which was good to see. This is a GIF of a range Doppler, which, of course, for me, because I did a radar signal processing as a PhD, this is kind of my bread and butter, we say in English. So the person was walking from radar 2, illuminating person walking from F to C. Because they're walking away from this radar, you're stretching the wavefront, so you get a negative Doppler. And what Bram was interested in, which is where all the clever work comes into it, he wants to get the PDFs. So when a person is walking anywhere in a room, the effects of the multipath with the different parts of the room, he can still extract the person's, it's a person, the fundamental statistics from the person itself. So when a person's walking around and the radar's illuminating, sometimes if your arm's up here, this becomes a corner reflector. If there's a strong reflector on that part of the room, the TV, it's going to be a strong reflection. But if you walk again to a different part of the room, you don't get that strong reflection. He wants to kind of extract the statistics caused by the target alone and not the multipath surrounding it, which is very complicated. And as you can see by this, that dominating yellowish color is the person. But if you keep watching, you see all these different detections that come around it. That's just because of the multipaths around. And he wants to be able to extract that fundamental behavior of the person alone and not anything that's in a complex environment. Sounds easy, but it's easier said than done. Also help with hardware user guides. We had a presentation by a guy who was working at a dance. They gave us a router that there's 4 antennas. You can steer the antennas 45 degrees. So I was able to create a document that done the complex response on my office where I am now, over all the antennas and all of the scanning configurations. So if you go to different parts of a room, this complex channel response will change. So that'll be interesting for the students to use. I did a hardware user guide for the 77 gigahertz radar also. Non-technical activities, I helped with some proposal writing. I found out how much of how dense and time-consuming those proposals can be, and especially when to compete with other people in these EU proposals, you need to have a lot of people from different countries, a lot of collaboration, and I think getting them to respond in time, and it's quite a tall order, we say in English. So I got to see that point of view whilst I was here as well. Thanks for your time. I apologise for going 15 minutes over. Any questions or comments?
Barry?
true time delay.
Yeah. If you want to make it, manufacture it.
Yeah.
So how is it manufacturable? I mean,
You mean on a portable device or in general?
in general, like
Well, you can
patch antennas.
you can have a huge coax cable. You can wrap them up, as long as the coax cables have a changing length at different elements, and you'd probably need a correct amplifiers as well to keep it the signal going along these long lengths. In practice, you need an adequate machining resolution. If we're talking about actual implementation at terahertz or millimeter wave, you're going to need microns, maybe submicrons, of constructing SIW, substrate integrated waveguides, and then having a change in that length.
So you
along
have different patch antennas, an array, and with different length of coaxial cables underneath, right?
coax cables, wave. I didn't mention this, but they also replied to me recently. Well, I contacted them a while ago. It's a German company. They sell optical delay lines. So optical delay lines can get large delays at low, because it converts it to optical. So you got the radio signal converted to light, and it's done in the fiber optics and then converted back.
So
That's expensive though.
Those coaxial lines are, what is the difference between the Butler matrix? Is it the same concept? Or?
Butler matrix is having, so you're including switches. So it's a routing problem, essentially, a Butler matrix in a way, because you've got different switch modes at different stages, and that series of switches allows a huge number of steering patterns by only changing a small number of inputs. I always get these confused, multiplexer or demultiplexer. It's one of those, a multiplexer or a demultiplexer. Small number of control inputs, large number of states. Essentially a Butler matrix.
Also, it is different with the leaky wave antenna, right? Or it's.
I did investigate leaky wave antennas. Leaky wave antennas are lossy, as you'd expect, because they're lossy dielectrics. They can do the same thing, because all leaky wave antennas are periodic. So if you've got a dielectric and you've got periodic openings in the dielectric, if you put a wave down it, you create like a beam opening pattern.
Different frequencies.
Same as this. It's very lossy.
It's less.
But I'll be honest, true time delay is only here because I've spent a lot of time on the first 5 months. Time modulated array is definitely the way forward, I think. Only if you get to 300 gigahertz and terahertz, and you want to be affordable, so you could just machine path lengths, and you don't have to change any. You don't have to put any FPGA or electronics in there, and you've also got the match gain in time, because if it's very narrow, the frequency, so you're only intercepting one subcarrier, should we say, you can't get any match filter gain in frequency, can you? Because all the other subcarriers you're not receiving. So that 5G synchronization code wouldn't work for true time delay arrays, because the code, the symbol isn't in time. You haven't got a code in the coded symbols aren't in time. The coded symbols are in frequency. But in true time delay array, you're only receiving one frequency for one angle. You're only receiving one symbol. You can't do no code compression. You understand what I mean then? But whereas the time modulated array, all of the subcarriers are at the harmonics, so you can compress the code over in frequency. There's lots of stuff. I'll point to if you are interested in like array stuff, array beam synthesis, nulling. Can I find it? It's time modulated array, and he recently become a fellow actually in the IEEE. The guy Xiwen Yang in Chengdu province. I can find it. I don't think I didn't put them in, but there's a guy Xiwen Yang in China. He's done a lot of work. There's a large capability with this, because this is just a simple on-off state. You can change your complex. You can put LCR circuits, RF impedances. You can make them decay at different times. You think about putting a discontinuous response and different impedances. You can make them decay at different times. So you got like a trapezoidal degree of freedom. And also you don't have, it can be on, but at path length, on, but at pi, phase pi, on, but phase pi over 4. So you can have different phases. It doesn't have to just be on one phase. It can be on phase 1, phase 2, phase 3. And probably with our caches subject, there's people that use evolutionary optimization algorithms. There's many of them now. There's like, what is the Firefly, whale optimization, grey wolf. There's loads of animal labels because that's probably where they're derived from. But they use these optimization problems to develop these. So you give a specification like, I want the beam pattern to be within this upper threshold and this lower threshold. Let the optimization converge through one of these optimizations, and it'll give you this pattern. And there's a whole, you can even, like, you know, the harmonics, you can actually, if you've got multiple phases on the on state, you can suppress certain harmonics. So you don't have to have all the harmonics, because the thing is, when you receive, harmonics aren't a problem because they're in your system. But when you transmit, you're transmitting power and you've got all those harmonics, you're going to cause a lot of interference. So harmonic suppression is important when you transmit energy, because you don't want to transmit energy and all these harmonics and cause unnecessary interference. So time modulated array is a very good topic, I think, and I wish I knew about it from the start, but there you go.
I propose that we take further questions, well, in the next 2 weeks, because you still are around.
Yeah, I'm joking. You can, whatever, as long as it's relevant.
So once again, thank you very much, Ben.
That's all right. Thanks for attending. Yeah, thanks for attending, and thanks for it was a daunting task, leaving my home country for the first time, but same weather.
Same weather.
So yeah, it was a daunting task. So it's been a pleasure. I've learned a lot, especially on this specific topic, and I can't really make excuses because arrays are a lot in radar as well. So, but I didn't really do much about arrays before. So yeah, and each of you have got different strengths. You've got different topics. So having conversations with you all and seeing what you're all doing in the lab has been quite interesting. And yeah, I wish you all the best in the future. I'm sure. I feel sure the group, even though it's a new group, and you've got a lot of competition with bigger groups around you, you've also got a lot of people from different harmonics radar, a lot of stuff Yang's doing, which is similar to what I've done, but also other topics. I won't mention Andreas leaving, but that was another one I would have mentioned. But you've got like a different avenues that you're going into, and I think that's important if you want to compete and also have connections. Anastasia, Andre, Yang have all got your connections in different parts of the world, and these are the sorts of ingredients you need to form a recipe to compete in modern research. So seems like you've got at least quite a few of those ingredients. So, but I wish you all the best anyway. So
thank you very much.
Regardless of my predictions, if they're right or wrong, I still wish you all the best.
Contributed, well, as you presented quite a lot of material to research that we did, and yeah, sometimes it's quite complicated with it. So
let's be honest though, Andre, you came to my office earlier and you said, Ben, I said an hour. I said, I might take an hour. No, I said, I'll definitely do it within an hour. And Andre went, well, questions 15 minutes. And I was like, no, I promised within an hour. So I didn't keep that promise.
But yeah, you're leaving now, eh? So do you already have some other destinations?
Well, I've got extended family in Canada. So Canada's the destination after this. I don't know what I'll be doing.